Thank you for coming. Like most of you, I used to be a Java developer. For 10 years, I worked with TDD, design patterns, solid principle, and then 2 years ago, I joined Big Panda and I switched to Functional Scala. And after a while, I realized that the way I was writing and reading code was very different. I was thinking way less, and in a good way. So my day as a Java developer would look like this. I would start with some code, and in my mind, I have a mental stack. And I start with a function, and it might throw an exception, it might not. So the thing I have to do is to go read the implementation, see the possible exception, put it in my mental stack, and go on. And then I would continue. I would read another function that would go to the database. And again, there might be an exception, there might be other kind of errors. So I would go to the implementation, put this in the back of my mind, and continue. And again, and again. So what happened at the end is basically overflow, right? Too much stuff to track, and that's something you don't want to do. So I'm going to give you a few techniques to avoid that. And we're going to talk about functions, about data, and then about patterns. And then we'll do a quick summary, and we have questions at the end. So the first tool I'm going to talk about is function signatures. The way I think about function signatures is this way, like a newspaper. So in a newspaper, you have articles and you have titles. And a good title should tell you enough about the content of the article. You shouldn't have to go and read the full article. So a good function signature should be the same way, right? So let's take a look at this function. What's going on here? Well, we have an input, it's an int, and we have an output, it's a string. So the way to visualize this thing would be like this. We have types, right? It's this circle, right? Ints and strings, and we have values. And values would be 1, 2, 3 for ints, or A, B, C, whatever for strings. And the function is simply the mapping between those values, right? And I don't really need to know anything about the implementation. What matters here is the function signature. When I see this visual, I get the full picture, right? So let's take a look at this function. What's going on here? It's the divide function. It takes 2 ints, and it gives me back an int, right? I'm dividing 2 values, and I'm giving you back 1. And if I give you 0, I throw an exception. So the way to visualize this thing would be like this, right? So I give you 2 ints, 5 and 5, and you give me back 1. I give you 10 and 5, you give me back 2, right? This visual is straightforward. But what happened if I feed it 0? What happened to the visual, right? Well, this thing happens. Well, there is an arrow that goes to some value that is not defined. Something not natural is going on here. Behind the circle, right, there is this exception thingy. And the way, right, that's a bad function signature, right? Why is it bad, right? Why is this function signature bad? Well, it lies. It doesn't tell you the truth. You have to go and read the implementation to understand what it does. And you have to keep this exception in the back of your mind. And that's only one function. Imagine a lot of those. You have to change those, and you have to put on top of your mental stack again and again. Well, you don't want that. So the way to avoid that is to use total functions. Total functions are very simple. For every single input, they have a corresponding output. So the visual is very clean, right? Here we have the increment function. I give you 1, you give me back 2. Give you 2, you give me back 3. It's very straightforward. The function signature is trustworthy, right? It doesn't lie to me. I don't care about the implementation. What I care is the signature here. And it tells me the truth. The trust is back. And okay, so let's go back now to the divide function. We'll come back to the divide function after. We're just going to move to the pure function first. This is the same function as before, right? The inc function here. That's the same, but something different happened here. What's different here? Is it a total function? Well, yeah, it's the same function. If I give you 1, it gives me back 2. But something else going on here. There is a printing in the middle here, right? And what is this? Why it doesn't look so bad right now, but it could be anything. Instead of printing, it could go to the database and drop the full database. It could launch missiles. The point is, I don't know from the function signature what this function does. Again, it's lying to me. So you have to go, you have to read the function, and then you have to put this in the back of your mind. This thing is called a side effect. So you want functions that are side effect free. And these functions are called pure functions, right? And when you use pure function, you think less about the implementation. What matters is the function signature, not the implementation. All right, so let's go back to this divide function, and let's try to fix it. So the way to do it, right, is to use this container type called either. And it will tell the reader of the function that there might be an error in the function, right? What it's doing, basically, it's bubbling up the internal of the function at the level of the function signature. This either type would tell you on the left side, that's the errors, right? And on the right side, the good value. So now, as a reader, I don't have to go and read the implementation. I can just look at the function signature, and that's it. I get the full picture here. Right? We're going to talk about these container types now. We're going to review the most common ones quickly, right, in the standard library in Java, in Scala. Sorry. So one of the most common one is option. So I would have a function like that, which is middle name. Not everybody has a middle name. And when I read this function signature, it will tell me there might be a return value or there might not, right? It's all about readability and to express yourself to the reader of this function. Either, we just saw it now. So when you have a function that returns an either type, right? Basically, this container type just wrap the simple type, right? That's what we do here. You see there is this brackety thingy. So inside, you put the type that you would like to return. And here, again, it will tell you this function might return errors. We have a list, and list is a little bit different. It's talking more about the shape of the output. When you read this function, right, it will tell you you might have multiple output values. It's a little bit different than before. We don't talk about errors. We talk about the shape of the output values. And then we have future. That's also very interesting. Future will tell the reader of the function that the value that is expecting might be or might not be available right now. It's more about when this value is available. All right, so let's recap quickly. We talked about total functions, and now for every input, you have a corresponding output. We talked about pure functions that have no side effect. And then we talked about container types, right? We saw how we fixed this divide function with either. And you have to, when you use all these techniques, right, you enrich your signature, right? You give a new meaning to your signature. Think about the newspaper, right? You want a good title. You don't want the reader to go and read the full article. You just want to give him a good headline. So good function signatures make you think less about the implementation. That's the whole point, right? The mental stack thing. You don't want to go and read the implementation every time. That's what I used to do in Java. Always, I would just to click on the function. Everybody is doing this. Look it up. What is it doing? You don't want to do that. You don't have to do that. When you use total functions, when you use pure functions, when you use container types, you have good signatures, and you don't have to think about the implementation. All right. Now we're going to talk about another property of functions. And it's a little bit different. This was a big aha moment for me in functional programming. It's not so much about if I care about the implementation, but more about how many ways could you implement the functions. It's very interesting. Think about writing the function signature, and I give you a pen, right? And there could be 10 pens. You don't know how to write this function. There are so many possibilities. So let's take a look at this function, right? And this is a parametric function. So we have here a parametric type, A. This thing tells you in the bracket, what it tells you that you could replace this A with any type. Could be a string, could be a long, an int, a list, whatever. That's what you have to think when you see this parametric type. And the question is, how many ways could you implement this thing? Could you implement this function? Of course, we're using total functions, pure functions. We don't use side effects. We don't throw exceptions. And we're restricting ourselves not to use all this magic hashcode function, toString functions, all this stuff that comes from the Object Java class, right? So how many ways? 2, 3, 4. Well, it turns out there is only one way to do it, right? And what's interesting here is why is that? Why is there only one way to implement this function? So the answer is easy. We don't know anything about A. This thing is so abstract that I don't know its values. If I tell you int, right, you can draw the circle of ints in your mind, and you know the value 1, 2, 3, 4. But if I tell you A, you draw this circle. You don't know its values. You don't know any function on A. So you put into a corner here. You have no choice. You have to return the input. You have only one way to implement that. What if I do that? What if I enrich the type signature with a container type, right, with list? I'm doing a small thing here. I'm just changing this A into a list of A, and I'm returning a list of A. So what I'm telling to the reader is the shape of the input could be multiple A's, and the output could be multiple A's. How is it going to affect the number of implementation? How many ways could you implement this function now? What did it do to the implementation space? Well, we can implement it a little bit more, right? We have a little bit more possibilities. We can switch the head and the tail. We can do some stuff, but not so many, right? We can't sort this thing. We don't have any ordering on A's, right? We can't sort the list. So what happened here, basically? We just enrich the function signature with a container type, and we get a little bit more of implementation space. The way for you to write this function is a little bit more, there is a little bit more ways for you to do it. And the last one would be to do something like that. What would this do to the implementation space of the function? What did I do here? I just remove the A as a return value and put an int, right? And think about it again. This int, you can draw it in your mind. It's a circle with the values 1, 2, 3, 4. So how many ways can you implement this? Well, 1, can return 1, 2, 3, 4, 5, the number of ints, right? So what happened here? What happened? Let's think about that. We just jump here to another dimension of number of implementation. That's interesting. We started with something very abstract, with 1A, right? And we had only one way to implement it. And then we enriched the signature with a list. We had a little bit more implementation possibilities, but not so much, not so much. And we finished with int, and we just jumped to another dimension. So what does it mean, this thing? Well, this notion is called parametricity, and it's very interesting. Why is it important to you? Because when you use a parametric function, right, the more it's abstract, the less way you have to implement it, the less possibilities for you to make a mistake, right? It's like giving you a blank page, and I give you 1 pen, or if I give you 10 pens. So you have so many choices that you could make mistakes. But here, when you use parametricity, the more abstract it is, the less you have to think about how to implement the function, right? It's not so much about what the implementation is with the function signatures. It's more about, for you, as a developer, how to write the code, right? You have to think less about it. Makes you think less about your implementation. So we talked about functions, right? About total functions, pure functions, parametric functions. But, of course, functional programming is programming with functions. But we all know that software is not only functions, right? Function, like software, is about designing data and designing behavior. It's beyond functions, right? There is something else there. If you want to build a full-fledged application, you can't just start writing functions. It's not going to work out. And is there a way, we're going to start with data. So is there a way to encode data that would make you think less, that would have this property for you as a developer to think less in a good sense, right? So the way to do it is to use sum types. Sum types is a way to encode data. So it's very simple. Here we have a developer trait, which is basically an interface. And you would have a DevOps, which extends this developer trait. Then you would have a full stacker with a salary in int. And then you would have an ML developer with a salary in long. And what does it really mean, this thing, right? Why would you want to encode your data this way? Why would you want to use this sum type pattern? This pattern, sum types, is also referred as algebraic data types. So keep this in mind. And why would you want to do that? Why would you want to use that? Why is it a good thing? Well, first, the compiler will be with you. When you use this thing, right, if I write a function, say hi, that takes a developer, and I pattern match on it, if I forget a case, the compiler will tell you you forgot the ML case, right? Something that is extremely powerful. In Java, the compiler will only check the syntax if you forget a semicolon or like a bracket. Well, in Scala, it will check the correctness for you, something that is very powerful. A lot of functional programmers will tell you, if it compiles, it works. Well, it comes from that, because the compiler is not only checking the syntax, but checking the correctness of your code. That's why they would say that. Also, these ADTs, these sum types, well, they're immutable. So you don't have to think so much about concurrency bugs, shared mutable states. You can't change this stuff, right? This developer, you can't really change it. If you want a new instance of it, you have to create a new one. So you don't have to think about all this possible mutable shared state. All right, so what about this function, the load user function? Well, you've seen it in a lot of code bases. These strings everywhere, these ints, this long, so you don't really know what it is. Right here, this load user could use the ID, could use the email. You don't know. You want to encode your data to make you think less about all these possibilities. You want the compiler to work for you. And the way to put some domain knowledge in your values, right? I want this load user function to take an email. So the way to do it is to use value classes. And basically, these value classes is just a simple pattern. You wrap your simple type, and you extend any val. And now you get a nice type, right? My load user takes an email. What does it do, really? Why is this thing important? Because you're putting domain knowledge inside your types. The compiler now will be behind you to catch you when you make a mistake. You don't have to think so much about what these strings, longs, what they mean, these doubles. Is it money? Is it time? No one knows, right? But if you type it properly with value classes, you don't have to think about that. All right, let's recap. We talked about ADTs, right, about sum types, and how they encode immutable data, and how the compiler will check the correctness of your code when you forget an edge case. There is basically there is no more edge cases. You don't have to think about forgetting a case. The compiler will do it for you. We talked about value classes and how we can just put domain knowledge inside the types, so the compiler will also help us to write code that is more correct. So all these techniques, right, about data will make you think less about the correctness. You don't have to think so much like before. The compiler will check the correctness for you. Something that I believe is extremely powerful and Java doesn't give you, right? All right. So we talked about functions, we talked about data, and what's left? Well, patterns, right? The way to design software in the old world would be like that. Design patterns. We all dread it. What are these design patterns? Well, they elaborate class hierarchies. Actually, they have good value, right? This stuff, if you used it, you see that it's very valuable. All these patterns do emerge in your software. You do see them. You do see abstract factories, visitors, and stuff like that. But, they sit in a book somewhere, right? Every team that you worked on, I'm sure you've seen it, will implement these patterns in a different way. Also, when you start learning those, it might have happened to me, you start using them everywhere. So what you get is all these over-engineered code bases. It takes a long time to internalize these patterns. So is there a way, right, and to fit this in your mental stack, all these patterns, it is not that easy, right? So is there a way to design patterns, to have patterns that would make you think less about, right? You won't have to fit all this stuff in your mind. So let's go back to the function world and try to do patterns at the functional level. Okay, so how would you spot patterns the old way? Well, you would look at your code, you would refactor, and then you will see a lot of similarities. So here it's the same thing. It's exactly the same thing. You have to look at your functions and try to spot the similarities, right? And what are the similarities at the function level? Well, the number of parameters, the number of outputs, the type, right? If the types are the same, the shape of the functions. So here I have 1 plus 1, A concat B, list 1, 2, 3 that I want to concat with list 4, 5, 6. So what does all of this stuff has in common? Let's try to find a pattern here. Well, they have the same number of parameters, right? I give you 2 ints, you give me back 1. I give you two strings, you give me back 1, right? So they have the same number of parameters. Also, the type is the same, right? I give you int and int, you give me back an int. That's the type of similarities you have to pay attention now, right? It's very different from design patterns. Now, you don't look at classes and hierarchies. You just look at your functions, at your types, at your parameters, and you try to see similarities. So this stuff, you would refactor it to this type of function, right? Combine ints, I give you 2 int, you give me back 1. Combine strings, the same. I give you 2 of strings, you give me back a string. Same thing with list. And what is the essence of this stuff, right? What transpires out of this pattern? How can you capture that? Well, it's this thing, right? You can feel it. It's one A and another A, and I give you back an A. It's one type, 2 of the same types, and I give you back 1. And how would you encode this thing in code? How would you do that? Well, the way to encode this is to use type classes. That's the way to extract the similarities at the function level. And type classes are not classes. They are traits, right? It's an interface. They have type parameter. We see here A. And the function that we wanted to extract here, this combined thing, is here. It takes 2 A's and give you back an A. It's very abstract. We don't have an implementation, but we can feel that this is the right encoding. And this is a parametric function. That's the tool for the job, right? A parametric function. It's very abstract, right? So, all right, now I have this stuff. What do I do with it, right? What do I do with this? How do I use this thing, right? It's so abstract. Well, one way to do it would be to implement instances. So it's very tedious, right? It's manual. You just do a new, and you override this combine with your own type. So here we do for int and int, and we'd supply the implementation for combining to int. Here we decided to do a plus. Same thing for strings, right? I override this combine method with string and string, and I give you back my implementation of it. You can also do it for your own types, right? Here I created my own class, foo, and it takes an int and a string. So I can also implement the combine method for foo, right? It's my own implementation, and I tell you how to do it. So I would take the first parameter and the second one, and would give you back a new foo. This stuff also, you can pay attention, use implicit. That's the way to do it. So why we use implicit? Because we want to summon the stuff and get it magically with the implicitly syntax, right? It's very nice. You see I give A and B, I get AB, 1 and 1, I get 2, and same thing for food. Great. Okay, that's a nice refactoring. It's very nice. But did we really gain anything here? Did we gain something, right, from the old way? Well, first of all, we don't use class hierarchies, right? All this scary, like, XML stuff just doesn't exist anymore, right? We work at the function level, right? So we didn't use any inheritance here, right? We just use overloading. We didn't use inheritance. And like design pattern, this stuff has a name, right? One of the strongest aspects of design pattern is they have a name. So if I'm in a team and I tell my coworker I used an abstract factory, it's supposed to know what it is. So the same thing with these functions, with this pattern. These patterns have a name. And this combinable thing that we just discovered, its official name is a monoid, right? So this stuff, right, all this, and that's not the only pattern there is. There is a lot of these patterns. And a monoid, it's the same thing. You see the combine method is exactly the same thing, right? Takes 2 of the same, give you back 1 of the same. It's the same trait. Also, it has an empty. We will need that later. But basically, for the plus, right, for ints, the empty would be 0, right? You want 1 plus 0 equal 1. So you need this. So great, but you know what? Well, you don't have to know this stuff, and you don't have to discover it. You can just import them. That's something that is extremely powerful, right? You can do that. You can import monoid from cat or from Scala Z. You can also import the instances, right? You remember I wrote them, right? For ints, for strings. Well, you don't have to do that anymore. You just get it for free from the library. And think about it, right? Think about how powerful this thing is. When you wrote design pattern, everybody would go to the book and would implement it its own way. There is no libraries for design patterns. It just does not exist. Here, not only you have the abstract interfaces, you also have the instances. Someone very smart wrote this code for you. You just have to take it and to use it, right? So if I import this stuff, I can do the same thing. I get this magical combine method on 1. On the value itself, I got this combine method. I can just use it. 1 combine 1, 2. Same thing on string. I did not have to write any code. This thing came for free. Right? Same thing for list. 1, 2, 3, 4, 5, 6. This thing is great. And of course, that's one pattern. But as Rob Norris would say, everything sufficiently polymorphic and useful already exists. What does it mean? It means everybody that worked on these patterns, right, they already discovered for you, okay? There is a big community out there that worked on those already and just supply this stuff for you in these libraries. You just have to look up the documentation, take what you need, and put it in your project. That's something that is very powerful, that does not exist in the old world. These design patterns don't have that. You don't have these libraries with implementation to use, and you can just go and take what you need. Also, because these patterns are so common, right, this monoid, there is a huge ecosystem building on top of these libraries. All these type classes, well, you can also get, you see this foo class that we defined before, and I had to write manually the implementation. If I want, I can use this library called kittens. I just import it, and it will magically figure out what is my monoid instance. It will give you magically this combine method for free, right? That's very powerful. All these libraries work with this functional pattern, so you get all this stuff for free. And this is an example, right? You could have, that's great about type classes. It's not only that you get this free thing, right, this combine, you also get a lot of what's called a derived function. So let's take a look at our monoid again. The combine method that we discovered is called the function, the definitive function, right? It's defining the type class. But we also have derived function. Sorry. We also have derived function. And this derived function here is, for example, combine all. This stuff you also get for free. And that's a very interesting, I just want to show you the implementation. You don't have to implement it, right? Because you get it for free, but that's the way to implement it. Think about parametricity, what we talked about before. The way, how many ways could you implement these combine all functions? How many ways? Well, not so many, right? You know you have to use this empty and combine. Look at this function. It's only defined in terms of these two abstract methods, right? About empty and combine. You know you have to use them. You know you get a lot of inputs. So you know, and you have to get one. So there is only one thing you can do, is to take all these values and hold them. That's it. To write this function is so easy because you don't have so many options. That's parametricity in action right there. So you can just import this stuff and you get this combine all for free, right? Now I can combine lists, right? I can give you 1, 2, 3, I will get 6. ABC, I will get ABC, and foos, and it works, right? So let's recap quickly about this functional pattern. How do you encode functional patterns? Well, you use type classes. These type classes have parametric function. And also, the way to implement these type classes would be to write instances. We saw that you can use cats or Scala Z and import it directly into your code base, and you don't even have to write your own instances. This thing will give it for free. Also, we saw that we have all these libraries that build on top of all these functional patterns. And something very important, right? All this knowledge, all this functional knowledge, you keep it with you. As opposed to Spring or Hibernate or whatever framework, these things does not get old, right? All these patterns, the way to encode functions, well, these things is forever. Whatever language you use, framework, these things stay with you, right? Throughout your career, you grow into it. And you don't have to think each time when you move to a new team, oh, I need to learn this, I need to learn that. Well, this stuff is universal. Right, so let's do a quick summary. We talked about function signatures, how you can use total functions, pure functions, and container types to write great function signatures, so you don't have to think about what is the implementation. The mental stack, again, you want it free of clutter. We talked about ADTs, right, about data and how to encode data in a way that would make you think less about the correctness of your code. The compiler will catch all your edge cases. And then we finished with with functional patterns, and now they would make you think less about, you don't even have to think about the implemented. You get them for free from all these libraries. You also don't have to think about all these class hierarchies that used to be in these old design patterns. You just get them for free from Cats and Scala Z. So use this stuff, right? Think less about your code. Thank you very much.